Thanks for watching Science with Mike. We're live today talking about light. You ever think about light? You should. Were you watching the fireworks and going, ooh, ah, and probably should be thinking, where does it come from, right? But first, let's talk about what light is. Then we'll talk about where it comes from, and then we'll talk about how light interacts with things. Okay? Take a look at that. That's an LED light. And what color is it? I just tricked you because you might have said white. But white is not a color. Light is all the colors put together in what we call the visible spectrum. Now these are spectral glasses, all right? And what it's got is a little diffraction grating in there. And so if I let you put them on, don't worry, it's going to be okay. I let you put them on. And then I show you the light. You see that it's kind of broken up into all the colors of the rainbow. All right? And you see red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv is how you remember the colors of the rainbow. But there's a lot of the light that you don't see. And so let's talk about the spectrum of light and the order that it goes. And then we're going to talk about what light is really in terms of how it's propagating itself through media. So let's take a look here at something we call in science the electromagnetic spectrum. All right? So, by the way, we got Addie here, my assistant. She's right over there. Sorry, I didn't introduce her. Anyway, here's what we can see. This is the visible portion of the electromagnetic spectrum, Roy G. Biv. Right? This is a very narrow slice. I didn't even have enough room to put everything else on the board. What you can't see is on either side of the spectrum. So next to red is infrared. Right? And you can't see that because it's invisible. It's not in the visible range. And actually, infra means lower than, so that's lesser energy than red. So you can't see lesser energy than red, and you can't see higher energy than violet, ultra higher than violet. So, and then over here you got X-rays, and over here you got radio waves and microwaves, and so on and so on. So here we're going lower energy. So red is the lowest energy part of the spectrum you could see, and then violet's the highest energy that you can see. And we're going to talk about how light is really a wave, all right? And so let's do that right now, all right? What I got here is what we call in science a long piece of rubber tubing. And what I'm going to do is I'm going to try to show you that the waves determine the energy, or the energy determines the waves, all right? You could do this splashing in a bathtub if you wanted to. We didn't want to do that today on Science with Mike. It would have been awkward. Can't get the bathtub in. Okay, so what we're going to do is we're going to go and we're going to take this tubing. And so I'm going to go right past you, Eddie. Sorry. I'm going to go past. Okay, sorry. Oh, and I got caught on stuff. All right. I'm going to put energy through this tubing, but just a little bit of energy. And you see sort of a start of a wave. But if I end up kind of wiggling it more and putting more energy in per time, you see that those kind of patterns, now I'm trying to go straight up and down. Those kind of patterns you get, the peak to peak, that's a wavelength. And if I do it real hard, then I get the waves to be closer together. Same thing with splashing in a bathtub. So the way we can kind of keep track of how much energy something is through the wavelength. All right? And so when you see red, that's lower energy. That's actually a longer wavelength. And if you see violet, that's actually a shorter wavelength. Violet has more energy. Don't think like weather maps. Weather maps make you think red has higher energy because red is warm. It's weather map world. It's backwards from wavelength. So violet is the highest energy. And so now let's talk about where light comes from. And then we're going to have Addie show you some examples of light emitting from things, just like they are in my LED light or anything. So we got to talk a little bit about what an atom is made up of. All right. So what you got is you got protons in the nucleus, you got electrons, and okay, it's pretty complicated. It's more complicated than this, but you can think of it as kind of like a circular orbit, but it's not. There's a whole field called quantum mechanics to tell you where electrons are, and it's very complicated, requiring higher math. And if you watch the movie Interstellar, Matthew McConaughey really can't understand it either. Okay? I mean, he had to keep asking Anne Hathaway all sorts of questions because it's that complicated. But if we simplify it so he could understand it, then what you got is you got the electrons can go into these circular orbits. If you put enough energy into anything, like Addie's going to do here, she's going to light a flame and put some substances into it. The electrons can jump out, and there's more than just 2 orbits here. There could be, up to 7. If this is hydrogen, it would have 1 proton, 1 electron. It can jump out to higher orbitals when you excite something, and that takes energy, right? Then when they relax, that's called promotion. And when they relax back down, that energy is given off in the form of light. So you get different kinds of wavelengths and colors with different things that have different numbers of protons and electrons, and these spacings and energy are different. So I'm going to douse the lights here, and we're going to look at some flame tests. So we've got some copper compounds, and is it copper? I forgot. Copper, and we've got some lithium compounds, and now we're going to watch what they do in a flame. Remember, when you put things in the flame, when you heat things up, you're pumping these electrons out to higher orbitals, and they don't stay there forever. They relax back down and give off light. So here we go. All right, I'll narrate. Addie has got some copper. What is it? Copper? I forgot.
Copper chloride.
It's copper chloride. There you go. Ooh. Yeah, there's copper. Pretty cool greenish blue color. That's one of my faves. Yeah. And that's how you could identify something. If you watch those crime shows, sometimes you see them doing flame tests on things. Copper will always give you that color. Next is some lithium chloride. What Addie's doing right now is she's taking just like a Q-tip, putting it in water, and then the solid adheres to it, and then that's pretty brick red, I guess you'd call it, brick cherry red. And so that's the color of lithium. And then you have other things. We don't have enough time here, but we have, like potassium will give you violet, and sodium will give you orange, orangish yellow, and so on and so on. Barium gives you a different color green. Strontium gives you a different color red. And so thank you, Addie. And the next thing we're going to talk about is how light interacts with things. Okay, so how does light interact with stuff? So let's say you've got something that has a color. All right, what color is my shirt? I tricked you again. I have a black shirt because black is actually not light, but it's the absence of light. And so what you've got is if you've got a substance that absorbs all wavelengths, then that appears black. And if it reflects all wavelengths, then that appears white. All right? So what we're going to do first is we're going to show you some different colored solutions and how they interact with light. All right? So we got a gizmo here, this LED gizmo. Okay? We've got basically one of our instructors made up the Spectrometer SCC1, is what we call it. And what you got are just different color LEDs. All right? You've got red and orange, a yellow, a green, something like indigo or blue, and a violet. You don't have indigo, you got blue and violet LEDs. Just like what you'd get at the electronics store or something like that. Now what we're going to ask is the question, like, why is this green? Why is this solution, it's just food coloring and water, why is it green? It's green because it reflects it absorbs everything but green. Or, okay, it's green because it absorbs everything but blue and yellow, which mix together to make green. So let's see why. All right. So you'll notice, and you might have to get in there real tight, and I might have to shut the lights off, actually, for them to see that. Let's do that. So, and, yeah, that's okay. Yeah, do another one, yeah. Now, when I place the green-colored solution in front of it, you will notice some of that disappears. I got to actually peek because I forgot. But you just get like the green and blue coming through. And what's happening there is the red, the orange, the yellow, and actually the violet is actually being absorbed. And that's why this solution's green. Okay? Yeah, thank you, Eddie. Throw the lights back on. Let's do red next. All right? This appears to you as red. And so the reason is it's basically absorbing all of the spectrum, but that near red. So let's go ahead with the lights again, Addie. Thank you very much. And you'll see that everything disappears, but, well, red, orange, and yellow. Okay? And you know, so it's a little bit lighter version, or it's a little bit orangish red when you look at this, and it's not deep red. Thank you, Addie. All right? And so it's really pretty simple. The colors you see are what's reflecting back at you. Everything else is being absorbed. My shirt's black because it's absorbing everything. And actually, we're going to do next, we're going to have Addie prove us that with a couple balloons. Okay? So why don't we do this, and then I'll man the lights, and then you can take... This is a laser pointer. Okay? This is a... It's okay. We're done with it. This is a laser pointer. So what we're going to have is we're going to have Addie use this laser pointer. This is actually a pretty strong laser pointer. My dad modified it so that it's milliwatts. That means it's probably not safe for people to... Okay, so now what we'll have is we'll have Addie shine this. You got to actually push those two connectors together right there. Oops. Okay, we'll have her shine that on the black one first. And then if it's focused properly, which I think it is, it should absorb a lot of that light. It's okay. I might have to focus it because it's got a little focus thingy on it. Okay, that's okay. All right, that's my bad. Oh, I'm going to hit Jason. Oh, geez. Okay, so you want to do another one? I think I got it. Yeah. So go right there, and then and if you had to, you could. There you go. Nice. And now do it with the white one. Pretty much nothing. Why nothing? I mean, you're at the same distance. You're doing the same thing. It's the same balloon. It's just that it's reflecting a lot of that light away. And so there you go. White reflects everything, and black absorbs everything. And I want to show you one more thing, and then we're going to take a little bit of a break. Because I want to show you now the particle size matters as well. So even though it has a color or not, if the particles get much bigger than a wavelength, you start having things that will absorb light no matter what, or scatter it. Now think about this. You got different solutions. This is green, but it's transparent. If light's not absorbed by it, so if you shoot anything in here that's green, the light will go through. I have a green laser pointer. And so I could prove to you that that's going through, right? And that's because the particles are much smaller than a wavelength. Now think about milk. Is milk transparent? No. If you shine light on it, it's actually not transparent. It's what we call a suspension. And so if the particles get big enough, ain't no light going through it anymore. And so that's one way you could actually find out the size of the particles with light. Light really is a very useful tool for helping us detect things we can't see. So I'm going to try to demonstrate that here with, maybe I should look over there, with this little thing I made up. If you go in like the gift store, right, they always got these little ocean things, right? And what that is that's alcohol on the bottom with food coloring in it, and that's heptane on top. And they don't dissolve in each other, but I can force them to be in contact with each other. But let me first show that same thing. This is a pure substance. It goes right through it. That green will go right through it. All right? But if I really agitate this and make it into what we call a suspension, all right, it looks like it's homogeneous, whatever you want. Someone said, you say homogeneous wrong, and homogeneous. It's supposed to be homogeneous. Okay, whatever. It's homogeneous, okay? But it's really not, if you look deeply enough, it's actually not going to let that light through because that is a suspension and the particles are too big. You might be able to see, if I shine it right at you, it's kind of scattering a lot where it's a suspension of a liquid and a liquid. And so if you take something where the particles are small enough, it'll be transparent to light. Your soda pop is transparent to light. Oh, darn, I kicked my laser pointer battery. That's okay, we got another one. And so basically that'll help us detect what's going on. If something's transparent, it's a solution, and that will be something that will end up being transparent to light. But if the particles get big enough, it gets blocked, no matter what color it is. So we're going to take a little break here, and then we're going to whip out the Foginator SCC1 after this.
Are you tired of this? Then it's about time you got yourself a Beaker. Beaker. Billy Mole's here to talk to you about the solution-containing power of Beaker. Made from high-strength, heat-resistant borosilicate glass, Beaker will make you the envy of your class.
All the other students are jealous of my Beaker.
And with these lines, you'll get your measurements right every time. Check it out.
Wow, look at those lines. Measurements correct every time.
Look at these burettes. In a side-by-side test, the one with the Beaker is less of a mess.
Wow, I love Beaker.
But if you act now, we'll throw in this Erlenmeyer flask. Erlenmeyer flask. Unlike Beaker, the angled walls of the Erlenmeyer flask let you swirl your solution. Swirl it harder, 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 all the way up until you have carpal tunnel. Aww. Tired of not getting attention from the girls? Well, wait until they see your Erlenmeyer flask swirl.
Hey, that's a nice flask.
Thank you. But wait, there's more. If you act now, in addition to Beaker and Erlenmeyer flask, we'll add these test tubes and test tube rack, Beaker tongs, safety glasses, a watch glass, a graduated cylinder, and much, much more. So don't ruin your sneakers. Get yourself a Beaker.
Thanks, Beaker.
Call Know Valve 3000. Don't use Beaker if it has a crack in it. Don't use Beaker if it has a chip in it. Do not carry Beaker on your head. Beaker. All right. Thanks to our sponsor, Beaker. One of my favorite products ever. Can't do without it. And okay, so anyhow, what we're going to do as our last kind of demonstration for you, I'm going to take something that's in between a suspension that blocks light and a solution that transmits light, and we're going to create a what we call colloid. This would be kind of like, you know, on a foggy day, you can barely see the headlights coming out or coming at you. What we got is we've got something specially designed for that called the Foginator SCC1 right at our handy fingertips here. So what we're going to do is it's basically, and if you have a fog machine, you could make your own fog juice. It's basically 25% glycerol in water. You'd probably want to use distilled water, and that's all it is. But glycerol tends to hang in the air. So if you're at a concert or something like that, you know, it'll actually kind of leave a trail wherever light goes and makes a really cool effect. So what I'm going to do is I'm going to take my laser pointer and we're going to see if we can just kind of bounce the laser off the wall. And it's pretty cool because you'll see the trail of it. And so there it goes. That means it's ready. So Addie, if you can deploy the power of the Foginator SCC1 by pushing that button. No, it might not be ready, is it? It's ready. Nope, it's not ready. So I'll keep talking. Maybe I'll just see if anybody had any questions. The Foginator's getting ready. It takes a while to heat up. It's a sophisticated piece of technology, and you can't force it to do what it doesn't want to do. And that's the thing. Science takes time sometimes, and you have to stall and talk like this while something heats up. Questions from anybody out there? Did anybody say any questions?
Yeah, Alex Parks wants to know, what do you know about string theory?
String theory? Here's everything I know about string theory. Okay? If you take rubber tubing, hey, what do you know? It's ready. The Foginator SCC1, did it go off? The light go off? Hit the button. See what? Nope, not ready. Oh, here's what I know about string theory. It confuses the heck out of me. Don't get me started, okay? You could tell I watched the movie Interstellar again with my kids. And it gets, don't even get me started on how gravity can warp time and gravity can suck in light, because I'm going to go on a tangent here, but everything has a wavelength, all right? So the funnier thing is that the more energy, the shorter the wavelength. And so, that's called the dual nature of electromagnetic radiation. Is if you serve a tennis ball, all right, that's got a wavelength too. And we know that because if you go lower than a wavelength of light, you can't see anything with a microscope anymore. But if you go and make electrons in a beam, you can actually make something that's even more powerful called an electron microscope, where you can see things much smaller than a wavelength. We good?
Yeah.
Okay, how'd that do? Stalled for time is what I did. Okay, so the Foginator SCC1 is at full power and ready to go. Hit it, and then what we're going to do is we're going to turn the lights out as this room fills up with glycerol, and I'm going to try to perform for you the triple bounce effect. See how I can see? Looks like a lightsaber, right? Oh, that's dumb. Okay, so let's turn out the lights, and then I will try. What I've done is mounted some lasers on the other side of the room, and as the glycerol kind of diffuses throughout the room, you can kind of see it filling up. Like it's more full over here. Oh, darn. Got to switch laser pointers. Got to go to the red one. You can kind of see the path of it better over here than you can over here. Nonetheless, let's see if I can go. I could bounce it. Hopefully not. Ow. Hopefully not right in my eye. That'd be cool. All right? And then you see, lasers are pretty cool things because you get one wavelength of light, and all the waves are in phase with each other. And so you get a really intense beam that stays intense for a long time. There you go. Now I'm bouncing it on the wall over there. Try not to bounce it on the camera. That camera is more expensive than my car. And there you go. So kind of cool thing. If you got a laser pointer at home and you got a fog machine, it's pretty cool. Be careful you don't hit anybody in the eye, for crying out loud. Okay, like I almost did myself. You lose a little bit when you bounce it off things. And so there you go. I guess we'll go back to the lights on, and I will say thank you once again. Not really. It's okay. Glycerol. It's like a vape lounge up in here. That's what's in vape thing. I don't know if you... I'm not that I'm endorsing that in any way, vaping. But it is like glycerol is what's in that vape juice stuff. All right. So thank you once again. Thank you, Addie. Thank you guys for watching. And we're going to cook up something for you next week. Same time, same channel. Thanks again for your comments, Alex, and everybody else. Science and honor. Peace out. Mike out.